Hello and welcome to the first part of the FusionScope webinar series. Today, me and my colleagues are going to tell you more about the newest tool by Quantum Design, the FusionScope, a correlative AFM and SEM in one tool. Before we get started, I quickly want to tell you a bit about Quantum Design. So Quantum Design was founded back in the 80s in San Diego. Today, it is not only a manufacturer, but also a worldwide distributor for scientific instrumentations. We have offices all over the world, which enables us to give you local support in our service centers. Today, Quantum Design has about 500 employees all over the world. Down here, you can see kind of an invention timeline of quantum design. So here on the left side, you can see where everything started with the MPMS and SQUID system. And on the opposite side, you can see the topic of today's talk, the FusionScope, which is the newest tool by Quantum Design. So just quickly, as I mentioned before, we have offices all over the world. Me and my colleagues, we are part of Quantum Design Microscopy, which is the newest addition to the Quantum Design network. We focus here on the further development of the tools for correlative microscopy. To give you an idea which parts will be featured in today's webinar, we will start with a quick presentation followed by a short question and answer session. After that, we will go into the lab and show you live how we measure with the FusionScope. And after that, we have another question and answer session. Anyways, at all times during the webinar, you can put your questions in the chat, which you can find at the bottom of the control panel. And now, without further ado, I will hand over to my colleague.
Yeah, also from my side, a very warm welcome. I now want to talk a little bit about the FusionScope and really tell you a little bit more why we believe that the FusionScope really opens a whole new world of correlative AFM and SEM microscopy. And before I go into the details, let me briefly tell you a little bit about the outline of that presentation. In the beginning, I want to give you a short motivation. Why do we believe that the combination of AFM and SEM in one tool is so beneficial for your research? Then I will spend a little bit of time talking a little bit more about the details of the FusionScope system, tell you something about the specifications, some USPs, and then of course also show you some applications that you can perform with the FusionScope system. After that, there will be some time to answer your questions. If you have any, so as Marion already said, please use the chat during the presentation to type in your questions. And then in the last part, we will show you a brief live demonstration of the FusionScope tool done by my colleague Lucas, who is at the moment already sitting in the lab in front of the instrument and will take over after my presentation. But let's start with the motivation. So why do we believe in this correlative AFM and SEM microscopy approach? And in order to highlight that, I want to start with a very easy sample that you can see here on the top, which is a silicon substrate that has two different types of electrodes. The yellow part are gold electrodes, and in between the gold electrodes, you have this blue aluminum electrodes. And if you now use this sample and put it in a conventional standalone SEM system that you can see here on the left, what you will get is what you expect, this typical black and white representation of your sample surface. You see the brighter parts in this case are the gold electrodes, and in between, you can barely see them, are the darker aluminum electrodes. Typically, all of the latest SEM microscopes also have an EDX attached. So of course, inside the SEM, you can also learn something about the chemical composition of this type of sample. And then in the EDX spectra, you will see here in red is my silicon substrate, and then in yellow you see here are my gold electrodes, and in blue here are my aluminum electrodes. If you now use the same sample and then transfer it to a conventional AFM setup that you can see here on the right part, you will learn something completely different about the sample. In this case, the AFM really gives you the real 3D topography of the sample surface, where you can see that the gold electrodes have a height of around 30 nanometers and the aluminum electrodes in between have a height of around 15 nanometers. And if you're working, for instance, with a conductive tip, you can also learn something about the conductivity of this type of sample. And here in the conductive image, you can see that only the gold electrodes show a conductive signal, since the aluminum oxidizes in air and does not show a high conductivity in the conductive AFM image. So as you can see, there are very complementary information that you can extract from both the SEM and the AFM. But typically, between these two worlds, SEM and AFM, there's a big gap. You always have to break vacuum. You need to take the sample out of the SEM, transfer it to the AFM, and then try to find exactly the same sample spot, which in some cases is very cumbersome and time consuming, or sometimes even not possible. And this is why we here at Quantum Design Microscopy developed a tool that solves this problem. And the first product that we launched 5 years back was the AFSEM system, where we integrated an AFM, a very small and compact AFM head inside a standalone SEM system, which then enables you in your SEM host system to perform this correlative AFM and SEM analysis. But today's webinar is not about the AFSEM system, but we want to focus on our newest development, the FusionScope. And with the FusionScope, we took this correlative microscopy approach to the next level, because here we are now not only integrating an AFM inside an already existing SEM system, but we merged the two microscopy methods in one completely new system. And you can see here how the FusionScope looks like. So a very compact microscope that both enables you to perform SEM and AFM at the same time. And just to tell you some basic features about the FusionScope. So to our knowledge, this is really the first true correlative AFM and SEM microscope that seamlessly integrates both of these microscopy techniques in one software interface and in one host system. It has a very compact vacuum chamber, which allows you to switch samples quite easily and fast and enables you to have pumping times of less than 5 minutes. So you can really easy and fast start your correlative measurements once you swap the sample. Talking about the SEM, there we are working with a very powerful Schottky emitter, and the FusionScope currently can work with acceleration voltages between 3.5 and 15 kilovolts. And for the AFM part, we have a scan range in X and Y of 22 micrometers and in Z of 15 micrometers. And one unique feature also about the FusionScope is that we are working with a very unique cantilever technology. We are using piezo-resistive cantilevers, so we don't use the classical optical detection to read out the cantilever deflection. What is also an important feature is the joint coordinate system. So both SEM and AFM work in the same coordinate system, and later on I will show you an example how easy then you can really target an area in the SEM image and then perform this correlative AFM image. If you're not talking about the FusionScope AFM measurement modes, it can really supply you all the standard AFM measurement modes that you would expect from a conventional AFM. We can, of course, do the classical static or contact mode imaging with the FusionScope. We can do the dynamic or tapping mode imaging, and we can also do the advanced modes like MFM, where we measure the magnetic properties with the magnetic tip, or target the electric properties by performing the classical conductive or EFM measurements. The FusionScope also has a very unique off-resonance mode, which we call the fire mode, that also enables you to measure the mechanical properties of your sample very easy and fast. So now let's take a look inside the FusionScope chamber. And in this animation, you see when we are opening the vacuum chamber, which is behind this red door, you see that we have this very compact vacuum chamber where all of the important parts are integrated. And in real life, it looks like that, which you see here in this image. And we have a few important parts inside the FusionScope chamber that I want to highlight. First, of course, we have here the pole piece of the electron gun that enables you to perform the SEM imaging. Then we have here on the right side of the chamber the AFM scanner that can be moved in X, Y, and Z. So you can also retract the AFM head completely out of the field of view of the SEM if you only want to perform the SEM analysis. Here in the middle, we have the sample, which enables you to work with the standard SEM sample packs, where you can very easily load your new sample. And then you also have this kind of U-shaped, what we call the trunnion, which enables you to tilt the whole sample and AFM scanner stage between -20 and +80 degrees. And how that can benefit your experiments, you will see in the previous slides. One very unique feature about the FusionScope is the user interface. I told you in the beginning that this is really the first tool that combines in one software interface all SEM and AFM imaging in one system. And the software really enables you to customize the user interface to your needs. You can work with a simplified view where you only target on the features that you're interested in. In this case, you see an example where you only see the parameters list that you're interested in, and also only work with the SEM image, and in this case, the AFM topography image. Or if you want to have more information about your images, you can also work in the advanced view where you can really customize which kind of AFM channels, in this case, topography, amplitude, phase, or 3D representation you want to show, the SEM image, also an oscilloscope or the infrared chamber camera. So this is really highly customizable to your needs. You as a user can really choose what kind of information, what kind of channels the FusionScope software should display. And you can then save this as a user profile so that the experiment is really always the way you would like to have it. The next very important thing is, as I said in the beginning, the joint coordinate system. And the joint coordinate system really allows you to locate an area of interest in the field of view of the SEM, and then you can automatically, by clicking inside the SEM image, perform a correlative AFM image directly at the spot of interest. And in this small recorded movie on the left, you will see how that looks like. So you have working in your SEM image, you find the area of interest. You can even move the sample, of course, to the area where you want to do the AFM scan. And then you can start the AFM scan directly at the spot of your interest and collect the correlative data. And then the FusionScope software also allows you to correlate the data directly in the software interface. And in the last part, my colleague Lucas will show you how you can do that easily in the live part of this demonstration. So really the FusionScope enables you to combine SEM and AFM data in a very intuitive and fast way to really add all of the measurements that you have done in one software interface. One of the very cool features of the FusionScope is what we call the profile view. And how profile view works, you can see here in this image on the left side. As I said, we are able to tilt the trunnion, which makes a tilt of the sample in combination with the AFM scan head up to 80 degrees. And this gives you this almost perpendicular view of the sample and the cantilever region. And this really enables the user to position the cantilever tip very precisely on the area of interest and also really see the cantilever tip while you're performing your AFM scan. And in this movie here on the right, you will now see in the SEM image when we do this tilting from 0 to 80 degrees. So in this case, we are working with a bone sample inside the FusionScope, and we are now rotating the trunnion from 0 degree to 80 degree, which gives you then access really nicely to the tip region. Then, of course, you can zoom in, and you can see that we can really perfectly see the cantilever tip that is now positioned on top of this very rough bone surface. And now you can very easily position the cantilever tip exactly on the sample spot that you want to analyze. And of course, it also gives you some feedback if the AFM cantilever tip is still okay, if it got blunt or if there's some dirt attached to the tip. So it tells you very very nicely if the user needs to change the AFM cantilever tip. And this profile view then enables you to really position the cantilever tip on the area that you're looking for. So if you're really looking for nanostructures on your surface, with the guidance of the high resolution SEM image, you can very easily position the cantilever tip on these structures. You can, of course, also watch while the AFM is doing the work. So you can really have the SEM beam switched on while you're performing the AFM scan. Or you can also locate, position the cantilever on demanding sample topographies, in this case, on top of these sphere structures, and then perform an AFM topography scan. One thing, of course, that we get asked a lot is how good is the performance of the AFM if you integrate it into the SEM high vacuum environment, because there you have running rough and turbo pumps, which can induce vibrations. And in order to highlight a bit the performance of the FusionScope, we performed this correlative imaging on single atomic steps of HOPG. So here on the top part, you see the profile view image of the cantilever on top of this HOPG surface. And then we can, of course, take a correlative image. And you see here now the single steps of the HOPG. And if you now look at the line profile that you see here in the 3D image, you can nicely see that we can observe the single atomic steps of only 0.3 nanometers in height change, which indicates really the performance of the AFM system, even inside the running SEM system. So we easily can observe single atomic steps since we have a noise level in the AFM of around 50 to 60 picometers. The next very important feature, of course, is the long-term stability or thermal drift in your system. And in order to highlight that, we performed another experiment. This is a silicon nitride membrane structure that on top of these holes has graphene membranes. So freestanding graphene membranes on top of these holes. And what we wanted to do is we wanted to see for a long-term measurement for almost 24 hours, how good the long-term stability of the AFM image is. And in this movie here on the right, you will now see all of the collected data over a total amount of time of 22 hours, how the drift of this AFM image area is. If I now start this imaging, you see that it's very, very stable. So over the course of in total 22 hours, we only observe a very small mechanical drift in the system. You see here now an overlay of a specific area, the first image that we took, and then the last image after 22 hours. And the total shift is around 300 to 400 nanometers. So this enables you to say that we have a thermal drift of less than 0.3 nanometers per minute, which is really state of the art for current AFM setups. So we have a high resolution AFM that is mechanically very stable, which enables the user really to perform high resolution AFM data with the combination of the SEM. Now in the second part of my presentation, I want to highlight a few applications that you are able to do with the FusionScope system. And the first one I want to show is what we call dancing on a razor blade. So the experiment that we performed here, we chose a very demanding sample, in this case, a wet shaving razor blade that you can see here. And we wanted to measure the blade radius of this razor blade. And you can see here in this image, the task is to position a very sharp cantilever tip on a very sharp and high aspect ratio sample surface, which is a very demanding task for a conventional AFM. But with the guidance of the high resolution SEM that we have in the FusionScope, this task becomes very easy, especially in the profile view, where you very nicely can see where you want to position the AFM cantilever tip. And we can even watch the AFM do the measurement. So here you see now, while we are doing the measurement of the blade radius, and then of course we can extract the 3D topography data of this AFM scan, which you see here. And then we can analyze the blade radius. So we have a line profile here on the upper part of this 3D image and on the lower part. And as you can see from the line profile on the upper part, we get a blade radius of around 30 nanometers. And in the second part, we get a blade radius of around 57 nanometers. So you can see that even for very demanding sample geometries, it's very easy to position the cantilever of the AFM precisely on the spot of your interest and then collect the 3D topography data. The second example that I want to show you is where we performed electrostatic force microscopy on grain boundaries of a barium titanite ceramic substrate. And this barium titanite sample is a very interesting sample for all kinds of automotive applications. And in this case, we worked together with the company TDK to really analyze for new barium titanite ceramic structures the energy barriers that you can measure between the grain boundaries of the specific barium titanite grains. And this is an experiment that you can only do if you really have the combination of AFM and SEM in one system. Because what we want to do is we have this barium titanite ceramic structure, so we need the SEM to identify the specific grains where we want to then perform the AFM analysis. And since we're doing electrostatic force microscopy, we need to work with a conductive tip. And here you see the cantilever tip that we are using, which is also a very unique conductive tip. This tip is fabricated by a 3D nanoprinting process called focused electron beam and deposition. And this tip is made purely out of platinum. And this enables us to create a high aspect ratio, pure platinum tip with a tip radius of around 10 to 50 nanometers. So a very high resolution conductive tip that we then can use to perform the EFM measurement. And for all of you who are not familiar with how electrostatic force microscopy works, I briefly want to introduce that. So basically what you do for an EFM measurement is first you work in classical dynamic mode to measure the topography in the first scan. So you scan the topography of your sample in the first scan, then you lift the cantilever up, typically by something like 10 to 50 nanometers. And this then gets rid of all the short range interaction forces that you typically have when the tip is in close proximity of the sample surface. And when you are in the so-called lift mode, you only feel a long range interaction forces. Then you apply a voltage to the conductive tip, and this then makes the tip feel the electrostatic interaction forces between the charged sample surface and the conductive tip. And this is then the information that you can then extract from the phase signal of your AFM scan in lift mode to learn something about the energy barriers on, in this case, this barium titanite surface. So how does the experiment look like? Of course, we started again with an SEM image where we identified the grain boundaries that we wanted to analyze. Then we can, of course, take a topography image that is directly correlated to the SEM region. And then if we now work with this EFM mode that I explained to you in the previous slide, we can apply a positive and a negative voltage to the tip. And you see that we can then measure different electrostatic interaction forces between the conductive tip and the sample surface. And then, of course, you can correlate all of this data, the SEM, the topography, and the EFM data inside the software to add all of this complementary information. And the work that we performed on the samples together with TDK was published last year in Scripta Materiala. And we could really show by using the combination of SEM and AFM in one setup that by inducing different silicon contents in this barium titanite ceramics, that the silicon-rich phase exhibits a smaller energy barrier compared to the phase where you have less silicon. And as I said before, this is an experiment that you can only perform if you really combine SEM and AFM at the same time in one system. As a last example, I want to talk a little bit about MFM, where we measured magnetic properties, in this case of an industrial duplex steel sample. And the experiment is pretty similar to the experiment that you saw for the EFM measurements. So again, we use the SEM resolution to really identify the area of interest on this duplex steel sample. In this case, we identified this area, and we did also an EBSD measurement. This was not done inside the FusionScope, but in a separate system. But this helped us to really characterize that we have these two different phases here, this austenite phase and that ferrite phase. And then very easily, you can, of course, find this same area again and then perform the AFM topography and the MFM measurement. The MFM measurement works similar to the EFM measurement. The main difference is that in this case, we are not working with a conductive tip and we don't need to apply a voltage, but instead we are working with a magnetic tip. But the measurement procedure is the same. First, you are measuring the topography, then you move the magnetic tip away from the surface and then only measure the magnetic interaction forces between the sample and the magnetic tip. And as you can see, we only get this nice magnetic domains on the ferrite phase, as you would expect it for this duplex steel sample, where in the austenite phase, you don't see any strong magnetic contrast. This then brings me to the summary of the first part of this webinar. I hope I could show you that the FusionScope is really a unique system where we, for the first time, combined AFM and SEM in one single standing system, which then enables the user to do real, true, interactive correlative analysis on the nanoscale. And I showed you 3 very short examples. One is where we performed a quality inspection to measure the blade radius of these razor blades. The second one was the analysis of electrical properties, in this case of a barium titanite ceramic surface. And the last example was measuring the magnetic properties, in this case for a duplex steel sample. If you want to learn more about other applications, you can also visit, of course, our website, www.fusionscope.com. And what is very important, we are always looking for interesting samples. I only showed you very brief examples what the FusionScope can do. But if you have some interesting samples in your lab or in your company, and you would like to see what the FusionScope can do, what kind of measurements we are able to perform on your samples, just reach out to us. We are always looking for challenging sample tasks and would like to show you the strength of the FusionScope system. And with that, we now come to the question and answer section. So if there are any questions from your side, please let us know or type them in the chat window.
You can either put them in a chat as mentioned before, or you can raise your hand and then we will unmute you and you can directly ask your questions. Okay, we have a first question in the chat. What sizes of samples does the FusionScope accept?
Yeah, so as I showed in the beginning when I showed you the FusionScope chamber, at the moment the FusionScope can work with a maximum sample diameter of 20 millimeters. So we can either work with the small or the bigger SEM stubs, but 20 millimeter in diameter and 10 millimeter in height is the sample size that the FusionScope currently accepts.
Okay, here we have another question. What are kind of the lab requirements to successfully perform measurements with the FusionScope?
So the lab requirements to set up the FusionScope are very easy. So this is really a difference to these big standalone SEM systems that you're typically used to in your lab. So all we need to set up the FusionScope in a lab is nitrogen gas and compressed air. So this, and then we need a power plug. So it's very easy and fast to set up the FusionScope. We have used the FusionScope and showed it at a lot of trade shows in the past months live, where we set it up even in very harsh environments, which is not optimal for performing SEM or AFM. But even there, you can easily set up the FusionScope. So all you need is really nitrogen and compressed air, and that's all you need to set up the FusionScope system.
Okay, here we have another question by, I'm sorry for pronouncing this wrong, by Mr. Saika. I will now unmute you. Can you perform CITS measurements with conductive tip?
Current imaging spectroscopy, tunneling spectroscopy.
So current imaging spectroscopy, you mean to take an IV curve at certain spots?
Yes, or the IDV curve.
Yeah, that's doable with the FusionScope. So we can do a mapping on this on the sample surface. So we can of course do the classical force volume mapping, but in principle this is also possible by applying a current and then taking IV curves at certain spots and then map that over the surface. That's possible.
Okay, thank you.
Here is another question. have you had any applications in the field of biomaterials or even biology?
Bella showed you in this profile view video that we inserted a bone, which I'm not a biologist, but is a biological sample. And of course, you can insert any sample that is vacuum compatible. Of course, like you have always this images like of this fly eyes or something like that. So you would need to take care about some charging of a biological sample. And at the moment, the FusionScope only operates in high vacuum. So we don't operate in environmental mode. This is a feature that is on the roadmap, and we will probably introduce a little bit later. But at the moment, it needs to be a sample that is high vacuum compatible when it comes to charging and also for vacuum compatibility. But in principle, if the sample is made for that environments, we can of course perform a correlative analysis. If you have some specific sample in mind, just let us know, and then we can discuss if we can perform a measurement on that samples. Yeah, freeze-dried samples. So the question is if freeze-dried samples, yeah, they work. Yeah.
Good, as we are anyway having another question and answer session at the end. I think that we will now move on to the lab, where our colleague Lucas will show you a more hands-on how to perform measurements with the FusionScope.
Yeah, hi, hello and welcome here in the lab. So for the next minutes, I just want to show you and bring you live into a measurement with the FusionScope and show you a little bit about how we can perform a measurement, what we can do to make a correlative AFM and SEM experiment. For this, I'm sitting here right next to a FusionScope machine, and I now would like to share my screen to directly jump into an ongoing measurement. I started measuring at the beginning of our webinar today, and then show you what we can see and what we can do with the FusionScope software when we do a measurement. So I now need the presenter mode. Okay, I hope that you can now see my screen and see that we are here live in a FusionScope measurement. And as a first step, I just want to show you what you can see here. So we have a lot of pictures, and I just want to briefly explain what they show. So we have here in the upper left 2 pictures. These are 2 different cameras. They are sitting here inside the FusionScope's chamber. So one camera gives an overview picture and one camera gives a more detailed picture, and we use them for a kind of a coarse approach to our sample. So we see here, this is the sample. So what we are looking at is an AFM cantilever. It's just on an SEM stop. And we are measuring this cantilever with, of course, another cantilever, an AFM cantilever. We see it here. On the more overview picture of the camera, we see here, this is the AFM head. This is our sample stage. And here comes the electron beam for the SEM. And so to magnify, like in the next step, we have here the SEM picture. So here we see a live SEM measurement, and we see here the AFM cantilever, and it's right now scanning back and forth and collecting the AFM data. And as I'm using here dynamic AFM, so amplitude modulation, we see the typical 3 pictures of the 3 observables of the AFM. So we have here the topography picture, we have the amplitude, and we have the phase. I show here the trace pictures, and of course you can have a look at the retrace pictures. They are all collected in one measurement. And every measurement we performed is saved automatically here in this list. You can see I collected some SEM pictures previously, and here are the automatically saved AFM pictures because I started, as I said, the measurement when we started the webinar. You can see here above these saved regions an overview picture. So this is an SEM overview of the sample I have loaded into the FusionScope. And here you see these small rectangles. they show the positions where I have collected some data. For example, here it's then highlighted when I mouse over, and here and here. So these are all SEM data I have collected here, and here comes the AFM data. So if you want to change what you see, you have here on the right side all the observables of SEM and AFM accessible, and you can customize the view here of the FusionScope software. So for example, if you say, I want to check the retrace picture of the topography, you can just drag and drop this into the field of view, and here you have the retrace and the trace picture of the AFM topography. So you can have it all in one software, and you can customize this for your needs. You have all the parameters of the FusionScope accessible. So here's a huge list of all parameters. You can look them up, you can change them. But if you do not need this, if you just want to do and focus on your measurement, you can just move this list away and focus on the measurement data. So what I want to do now is I just want to stop the AFM measurement and show you how it looks like when we go into the profile view of the FusionScope. So here I want to focus on the SEM picture. I just zoom a little bit out like this. And I use this position tool here to turn the view to 80 degrees. And then we can have a better look what the cantilever is doing when it's scanning over the surface. So you see here in the optical camera view, it's now tilting. At around 60 degrees, the cameras are blocked, but we have the SEM. And here we can very nicely see our sample. So the cantilever we are measuring with the cantilever. So like this. I zoom a little bit out. Again, I zoom a little bit in so that we can now start the AFM measurement again and can really see how the cantilever approaches and how it looks like when the AFM is scanning the topography. So we want to measure this little hole here. I hit Start AFM Scan. The cantilever goes to the 0 position and now approaches to the surface. As the sample position was a little bit retracted, it was going one step to the top direction to place the piezo of the cantilever in the middle position so that we have the highest accuracy. And now we can really nicely see how the cantilever is scanning over the topography. And we can look at the topography here and see how it is measured line by line. And we can control this measurement here in the SEM. We have different possibilities for processing this data live. So for example, if we would like to have a different fit, for example, a line fit, we can just click here and have a line fit for the data, or we can go back to the plane fit if this is more suitable for the data we have here. And of course, what we can do is we can change the view, we can change the color scale as you want it to look like, or we can look at a 3D representation of our data, and we can do this live and look how the data is acquired here. Of course, we can have a more closer look into our data. So for example, when we want to have a more closer look to the SEM data, for example, we can just change here the field of view in the software and put this into a single image mode and just move this window away. So here we have a real nice view into what's going on here. Now, I would very much like to make a more high definition picture of the SEM. For this, I just stop the AFM scan. Cantilever stops, retracts a little bit, and I can hit here in the top an HD button. And now the SEM is collecting a more high resolution picture of the data we have here, or of the sample, of the position. We can very nicely see the cantilever here. We can see the structures we are measuring with the AFM. And the data acquisition is quite fast. So in under 1 minute, we can collect a high definition SEM image. And the next step I want to show you is how it is possible to correlate images, how to overlay different observables, so SEM and AFM data. So for this, here you see the picture we now collected here in the SEM. For this, I just go back to the grid view so that we have all our data in one screen. And I just open up a picture I've previously collected. So for example, this SEM data, I just move it at some window and I say, okay, I just want to correlate this data. I hit this button, say correlate frames, then I can choose with which data I want to do the correlation or the stacking of the images. So let's choose this topography image here. Aha, now it automatically correlated it. And we see, ooh, there's a little mismatch. But this is no problem. We can compensate for this. So we choose adjust overlay. And we choose some control points here in the SEM, for example. And we drag and drop the AFM data here, and it more or less nicely fits. Maybe change a little bit like this. Okay, so now it is very nicely correlated with different possibilities to look at this data. We can have a stack view or an overview picture. And if we think, okay, this is nice, we can close this and of course export this data as an image, JPEG, PNG, BMP, whatever. So this is possible. And of course, the data of the AFM you can export in video native file, for example, to do your own post-processing of the data. So I've shown you how easy it is to correlate data. And maybe as a last thing, I would like to show you how you can find a different spot on your sample, how we can do this. To do so, I just start the SEM again. Put this here, do a live picture. We go back to 0 degrees so that we can have a top view of our sample. The trunnion is moving. Oh, I can activate the camera again so then we can see what's happening inside of the chamber of the FusionScope. Zoom a little bit out so that we can see more of our sample. So now we want to choose a different position on the sample. So what I do is I move the I move the AFM out of my view as I retract AFM. So the AFM retracts, and now I can just double click into the SEM picture, for example, like this, and it moves to this position, and I can maybe zoom in a little bit more, choose more precisely which position I want to measure. This one, for example. I can do a high definition SEM picture and then just hit the start AFM button. The AFM moves to this spot and starts the AFM imaging. So this is more or less the basic principle how we can perform correlative AFM and SEM measurements with the FusionScope. So I just wanted you to give a brief introduction in how these measurements are performed. And yeah, I would think if you have any questions to these measurements, how they work out, you are free to ask the questions now. And I think we will have a more in-depth webinar about the measurements or different kinds of measurements in the FusionScope in the next weeks.
Yes, that is kind of the last thing that we want to mention before going into the second question and answer session. So we will just share. We just want to mention once again that if you want to learn more about how correlative microscopy can benefit your research, feel free to contact us and send us your samples. We are very happy to demonstrate what new insights you can gain by using the FusionScope for measurements. Other than that, on the 17th of May, we will have the second part of the FusionScope webinar series, which is a more in-depth demo. So we won't have a presentation at the beginning, but only do a demo showing you really step-by-step what steps do I need to take before I can take my first correlative AFM and SEM measurement. Other than that, we are also present at quite a few shows with FusionScope where you can really visit our booth and try the FusionScope yourself. The next possibility for that will be the Control Conference in Stuttgart at mid-May. Anyways, there's always new information on our website, fusionscope.com, and on our social media profiles on LinkedIn. So I think we already have the first question for our second question answer session. So can you do force spectroscopy as well as imaging?
Yes, we can do both force spectroscopy and force imaging. So this is also implemented in the FusionScope software. And then, like Lucas already showed, you can then export the data into any file format that you would like to use the data. So this is something we can do with the FusionScope measure mechanical properties. But on top of that, we also have this fire mode that I briefly introduced in the beginning, which enables you also to measure the mechanical properties on the fly. So we can do both the classical force volume or force spectroscopy. And on top of that, we also have the fire mode for measuring mechanical properties.
So another question, that's a very good question. Where's your demo site? I think we forgot to mention that. So we are located in Darmstadt in Germany, that's close to Frankfurt. We have a demo site here where we also do most of the customer sample measurements, but of course we also have an application lab in San Diego.
So feel free to visit us. So if you like to drop by with your sample, you're more than invited. Either if San Diego is closer, probably it's closer to come to Darmstadt, but we are always happy to have visitors and demonstrate the tool here in our demo lab.
Have you got a site in the UK? Not yet, I would say, but we are going to 2 shows in the UK, the MMC in Manchester and another show in Birmingham. Oh, here's Satyam, he probably knows better, so we'll unmute him quickly. He's our FusionScope sales representative for the UK. So you are unmuted, Satyam, now.
Just to answer your question, yes, so we are actually attending 2 shows, the Advanced Materials show at the end of June and also the MMC show at the beginning of July. But we're also organizing some workshops in the week of the 20th, so the 21st and the 22nd of June, and that will be in-house in Leatherhead at our Quantum Design UK facility. So we'll obviously send you more information as well. So if you reach out to us, we can let you know the exact dates. Thanks. All right, thanks, Marion.
Thank you. So we will surely send you the information.
Good. I think we see no more questions. Then from the whole team, thank you very much for attending this webinar. We hope you enjoyed it. If you have any additional questions that pop up, just reach out to us or write us a short email. And we hope to see you again on the next webinar, 17th of May. And hope to see you also at one of our trade shows where we show the FusionScope live. So thanks for attending and have a great day.